Hey Algebra 2, if you've wondered why we're doing logarithms and what is the point, which you guys may have actually been wondering, today we're going to talk about it. And I'll write down as many notes as I can about the stuff I'm just going to talk about, not the computing number part, but the wordy part. And hopefully you'll feel awesome because you'll know why we're doing this. So first of all, if we pretend like we're living in a time long ago, when logarithms were actually discovered. It's really before calculators and before computers. During that time, scientists, merchants, like salespeople, sailors, needed to make calculations for both astronomical observations, and navigation. Logarithms made these calculations much easier, believe it or not, easier, faster, and more accurate. Please remember, you can always push pause at any point in the video if I'm going too fast for you, right? So logarithms made the calculations much easier, faster, more accurate than just calculating with large numbers, all right? Let's see what else I want to tell you. Well, there's this guy, a mathematician named Pierre Simon Laplace, but pronounced probably much fancier. He's from the 1800s. He said that logarithms are an admirable artifice which, by reducing to a few days the labor of many months, doubles the life of the astronomer and spares him the errors and disgust inseparable from long calculations. Whew. So he was really happy they were out there. A typical table of logarithms. A typical table of logarithms, like the table that we've been using, has many rows of numbers. Arranged in 10 columns. Okay, the numbers in the table are decimals. That's an I. The numbers in the tables are decimals. In our table, they are given to 4 decimal places. And there are 90 rows of them. Okay, some tables of logarithms have 900 rows. Okay, down the left-hand side of the table are the numbers from 1.0 to 9.9. And across the top are the numbers from 0 to 9. To read the table, you locate the number whose logarithm you want to use using the numbers down the left of the table, followed by the numbers across the top. So we're going to go down the left of the table first, and then across the top second. All right? So if we look at this table, let's just look. Like, what does the number in the third row and the second column represent? I'll circle it. So third row and second column. Okay, what does that represent? That would be the representation for 1.21. Okay, the entry, let's say it that way. Let me move that over. The entry for 1.21. Now what does that mean? Okay? So this would be the logarithm of 1.21, which is approximately 0.0828. All right, whatever. Let's go. Just follow along for a little bit. So the logarithm of numbers larger than 9.9, which aren't on this picture I took, and smaller than 1.0 can also be found using this table. Okay, suppose you want to find log of 365. Suppose you wanted to find the log of 365. Is there a way you can rewrite 365 to include a number between 1.0 and 9.9? How? Well, I can easily say that this is the same as log of 3.65 times 10 to the second, right? Oh yeah, we can do that. And I can rewrite that to say 2 plus log of 3.65. I know I'm writing all over my picture now, but it's okay. That's not awfully important. Just doing a little bit of review. Okay, now all we would have to do is find the log of 3.65. So let's look at our table, right? What is the value of log of 3.65? So let's look. I've got 3 point, oh, it's not on this picture. Hold on, going to a new page. Remember, we were looking for log of 365, which we can do finding log of 3.65 times 10 to the second, which is 2 plus log of 3.65. Well, I found it. So 3.65 is right there. So that's going to be 2 plus 0.5623. 2.5623, right? Pretty cool, pretty fast. How would we find log of 0.365? Well, I could find the log of 3.65 times 10 to the negative 1, which would be much easier, right? Because now I'm just 2 decimal places, so that would be negative 1 plus log of, that'd be negative 1, ooh, forgot to grab my eraser, negative 1 plus the same value, 0.5623, which does in fact equal 0.4377. Cool? So that's why log tables were used back before we had calculators, right? We could move things into scientific notation and find the log of them. Let's practice a little bit more, though. Let's make this useful to you in an odd kind of way. Find the product of 3.42 times 2.47 without using a calculator. All right? Whew. I'm going to push pause, if you don't mind, because really, this is not going to be pretty. Be right back. All right, to prove a point, I made a mistake. All right, so I have to do it again. Pause. That time I got it right. Okay, that took me way too long, right? You're rounding, no, you're not rounding, you're like carrying and way too much time. And that's just multiplying 2 small numbers, okay? How can we use logarithms to find this product? New slide. Be right back. Now if we take the logarithm of the product, we can rewrite it as a sum of logarithms, right? That's one of the properties we learned, 3.42 plus log of 2.47. you can look up in the table of logarithms, the last two pictures that I showed. If I look at, let me grab it, 3.47, or sorry, 3.42. So I'm going down to 3.4 and moving over 3 columns to 2. That's 0.5340. 0.5340. And then 2.47, so I'm going to 2.4. Over to 7, 2.4, over to 7, 0.3927. Oops. 0.3927. Is that what I said? 2.47. Yep. 0.3927. If I add those together, it's much easier to add than it is to multiply. I've got 7, 6, 9, 10, 11, 12, 8, 9. 0.9264. Right there. Now, if I look at my handy-dandy chart for 0.9267, it's on the back side of it, 0.9267. I could probably push pause. 92. Still looking for it. If I find on the chart 0.9263, that is 8.44. So log of 8.44 equals 0.9267. So exact number not quite right? But 8.44 is that, let's see, what's the next one? 8.45 is 0.9, oh, no. That one's 3. And this one is 0.9269. So somewhere in between those two, right? Okay, which one's closer? That one is actually closer. Oops, I erased it. That value is actually closer to the actual number. So since log of 3.42 times 2.47 equals log of 8.45, log of 3.42 times 2.747 equals log of 8.45, what can we conclude about the approximate value for 3.42 times 2.47? Maybe if I write it like this, you'll, unless you've already like, whatever, Miss Carly, we got it. I can say this equals log of 8.45. Okay, we've talked about it a few times. If I've got log on both sides, I can cancel them out. And we know that this equals that. Okay, pretty close, right? It's a good approximation. And what's cool is I don't have to make any multiplication mistakes, so I didn't have to do it twice. Okay? Pretty awesome? All right. Let's do another one. What if we had to calculate 3.42 times 10 to the 14th times 5.76 times 10 to the 12th? Goodness, what do we do here, right? Well, let's go for it. Take the log of it. Log of 3.42 times 10 to the 14th times 5.676 times 10 to the 12th. Okay, let's use our properties of logarithms. That gives me log of 3.42 plus log of 10 to the 14th plus log of 5.76 plus log of 10 to the 12th. These are easy. I'm going to move those to the beginning. So I have 14 plus 12 plus log of 3.42 plus log of 5.76. I'm going to look these up on my handy dandy little table, and I'll be right back. here I have 0.5340, and here I have 0.7604. So if I add all four of these together, I get 27.2944. What do we do with that? Okay, I need a new slide, sorry. So we are at 27.2944. I can actually split that up into 27 plus 0.2944. And what does that mean? Well, if we're taking a log of something, this is like log 10 to the 27th, right? So we need to figure out what this is the log of. Log of what equals 0.2944. If I go to my handy dandy table, 0.294, ooh, there's a 0.2945. So log of 1.97 equals 0.2945. That's pretty darn close. I'm pretty happy with that one. So if we're at log of 1.97 times 10 to the 27th, that's like saying 27 plus 0.2945, which is 27.2945. Pretty darn close. So, therefore, as a final answer, our first problem said, what are these two numbers multiplied together? We just said that it is approximately 1.97 times 10 to the 27th. Final answer. Okay, so with a logarithm table, it actually is easier to calculate large numbers. Believe it or not. I lied. I have one more. What about dividing large numbers? Okay, I'm going to cut and paste a problem over here. Hold on a second. All right, I know we're doing a lot of problems that aren't actually in your packet, but it's really awesome to be able to tell you what logarithms were used for. Like I said earlier, I was never told why, and I never asked, but it's just really nice to be able to know why. So let's try this one. This is our last one. Then we'll do exercises, and you can start your problem set. According to one estimate, the mass of the Earth is roughly 5.28 times 10 to the 24th kilograms. Who knows what amazingly smart scientist figured that out. And the mass of the moon is about 7.35 times 10 to the 22nd kilograms. Without using a calculator but using the table of logarithms, find how many times greater the mass of the Earth is than the mass of the moon. So really what we're doing is taking the mass of the Earth and dividing by the mass of the moon. Yikes. Right? So I could say this is R, which is the ratio of the two masses. Okay, let's simplify this, because that'll be really nice. We have 5.28 over 7.35 times 10 to the second, because if I've got 10 to the 24th on top and 10 to the 22nd in the denominator, that simplifies to 10 to the second. Now if I take the log of that, I've simplified even further. That gives me 2 plus log of 5.28 over 7.35. Now we learned a property about a fraction with a logarithm. It's the same as subtraction. Log of 5.28 minus log of 7.35. Now, handy dandy table. I've misplaced mine. There it is. Give me a second. I'm going to look these up and I'll be right back. So there we go. Those are the two values. Now I can take 2 plus 0.7226 minus 0.8663 and get a final answer of 1.8563. Now let's look for this in my table. I'm going to rewrite this whole thing on the next slide. 1.8563. So I'm looking for 0.8563 in the table. To find out the log of what equals 0.8563. Where? So I've got 7.18 equals 0.8561, and 7.19 equals 0.8567. I'm looking for 8563, so I actually think this one is closer. So that means that log of 7.18 times 10 to the first is the same as log of 71.8, right? Equals 1.8563, approximately. I should have that approximate symbol there, right? So I can say that the mass of Earth is approximately 71.8 times that of the moon. Okay, that was a lot of work, but fun. Now we have exercises. Let's see, there's actually quite a few that you can do to practice. I'm going to go ahead and work them out and not record. And I'll point out any crazy things that I find, but this is just a lot of practice. For instance, this first one, remember when I have log on both sides, I can just cancel that out and say x squared equals 49, x equals plus or minus 7, and then check for extraneous solutions. Okay, so go ahead, work these out. Both of these are valid though, so that works. None of them are extraneous. But I'm not going to record every single one I do. We'll just push pause and check your answer. Cool? All right, I'm pushing pause and checking my answer. All right, push pause and check it out. Both of these are valid. If you plug them back in, you don't get a negative number. Life is grand. Another one, be right back. Cool, this one works too. Checking my solution got a little hard at the end, but I just forgot to distribute that x again to check my solution. So it is a valid solution. Life is grand. Let's try D. Be right back. All right, check this one out. I got two solutions, plus and minus 2. First I checked x equal 2, and it worked for all of the logarithms in the problem. Then I checked x equals negative 2. It did not work for that one, so I had to throw it out. If it doesn't work for one, then you cannot use it. Cool. Another one. This one's a minus. Let me give you a clue though. Rather than do a division because I have a minus, I moved it over there and made it a plus so I can multiply this side of the equation. Cool? Okay, now I'm going to push pause again. All right, I got an answer of x equals 6 over 4, which simplifies to 3 over 2. I checked it out in the first logarithm in the problem. 3 halves squared is 9 fourths. Minus 3 halves is less than 0. So that solution does not work. Therefore, there are no solutions. Because we only got one, and if it doesn't work, we don't have any more to check. F. Nothing crazy about this one. Lots of multiplication. I would move this into the exponent spot so I could cancel out my logs. I'm going to push pause. Push pause. I got x equals 0, which if I plug that in right there, log of 0 is undefined, so no solutions. Okay? All right, let's try this one. If you notice, I have a negative in front of the log, which I would move to the exponent spot. So I'd have log of x minus 4 equals log of 1 over x minus 2. Now I can cancel out my logs. X minus 4 equals 1 over x minus 2. I really like cross multiplying when this happens. So I get 1 equals x minus 4 times x minus 2. Go ahead and FOIL that. X squared minus 6x plus 8. Try to solve it. I have x squared minus 6x plus 7. And I can't factor that. And I'm sad. Okay, big time bummer. We have that cool thing called the quadratic formula though. So let's plug it in. Negative b plus or minus square root of b squared minus 4 times a times c all over 2a. 6 plus or minus the square root 8 all over 2. 8 is 4 times 2, so I can take out a 2. If I simplify this way, I've got 3 plus or minus the square root of 2. I can't just willy-nilly cross this out, but if I factor out a 2, I get 3 plus or minus the square root of 2, and then I can cancel it with the denominator. Let's check our answers. Yes, we all get sad when we have to do the quadratic formula, but it's okay. It's not hard. It's just a little putsy. I'm going to check x equals 3 minus the square root of 2, all the way up here again. 3 minus the square root of 2 minus 4. So if I take this and I minus 4, I'm going to get a negative number, right? That's not a good one. But now let's check x equals 3 plus the square root of 2 minus 4. So all I did was replace that for x. This one gives me a positive number because 3 minus 4 is negative 1 plus the square root of 2 is greater than 0. Need my calculator. Square root of 2 is 1.414. So 3 plus the square root of 2 minus 4 gives me a positive 0.414 with a lot of digits. So that is the only one that works. This is an extraneous solution. Cool? All right. How do you know if you need to use the definition of a logarithm to solve an equation involving logarithms as we did in lesson 15, or if you can use the methods of this lesson? If the equation involves only logarithmic expressions, then it can be arranged. Like if you can do log x equals log y, then we're good to go. We used that in 15 too, though. We did that a lot in 15, so it works well. If there are constants involved, then the equations can be solved using the definitions and the properties of logarithms. So we're just going to use any method that works every single time. And there is your summary. Okay, read through it. It's what we learned. Lesson 15 is the last section in our logarithmic section, so we're going to have a quiz and then a test. So just make sure you understand how to do everything, and it takes a lot of practice. This stuff isn't difficult, but it's a lot of information all shoved into just a few days. Nice work.